In this lecture, I'm going to be talking a little bit about hyperbolic functions. So hyperbolic functions are these 6 hyperbolic trig functions. And in a little bit we'll see why they're given this name of hyperbolic. One reason for giving names to these functions that have this form is that functions of the form e to the x minus e to the negative x and e to the x plus e to the negative x come up in lots of different applications. So there's a reason to have a special name for these types of functions. But when we say we have a hyperbolic sine function, we mean that sine h of x, or hyperbolic sine, is defined as e to the x minus e to the negative x over 2, and that hyperbolic cosine is defined as e to the x plus e to the negative x over 2. So what we want to remember with these two different forms here is what they have in common and what the differences are, because really, I mean, we need to know all 6 of these hyperbolic functions, but everything is based on these two definitions. So if we know our definitions of hyperbolic sine and hyperbolic cosine, we can generate the definitions of these other functions as needed. So notice that both hyperbolic sine and hyperbolic cosine are a sum of powers of e. They're both divided by 2, and the only difference here is the sign. Okay, so that hyperbolic sine has a difference of e to the x and e to the negative x, and hyperbolic cosine has a sum. One trick you could use to remember this is, I think sine is sin, and that's negative, so maybe that helps you remember that there's a negative sign here, and that cosine, hyperbolic cosine here, has the plus sign. The other definitions of these hyperbolic functions should look similar to how our regular trig functions are defined. Hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Hyperbolic cosecant is 1 over hyperbolic sine. Hyperbolic secant is 1 over hyperbolic cosine. And hyperbolic cotangent is cosine, hyperbolic cosine, over hyperbolic sine. Okay, so we want to take a look at what these graphs look like and then start seeing how we can use these definitions. Okay, so here I've got graphs of 3 of our hyperbolic functions. This first one here is hyperbolic sine. Okay, so we can see that the domain of this function is all real numbers, and its range is also real numbers. And remember that this graph is the graph of e to the x minus e to the negative x over 2. It just has this name of being also called hyperbolic sine. This second graph on the right is our graph of hyperbolic cosine, okay, which we know is e to the x plus e to the negative x over 2. It's the graph of that function. And we can see that the domain of this function is all real numbers, and that its range is numbers that are greater than 1 to infinity. Okay, and the other picture that I've shown here is our hyperbolic tangent. So hyperbolic tangent here has asymptotes at 1 and negative 1. So the domain of our hyperbolic tangent function is, again, all real numbers, but its range is from negative 1 to 1. Okay, so we're approaching negative 1 as we go to negative infinity and approaching 1 as we go to positive infinity. Okay, so we're going to want to look at a few examples to practice using these definitions. So let's just start with what we often did first with our trig functions. We found values of the trig functions for particular values of for particular angles. Here we've got for particular values of x. So if I look at hyperbolic cosine of 3, or cosh of 3, I'm looking at e to the third plus e to the negative third over 2. So there's not much I can do to simplify that. Again, remember, hyperbolic cosine here is e to the x plus e to the negative x over 2. And then if I wanted to do something like hyperbolic cosine of natural log of 3, I can see I'm going to be able to use some of my properties of e and natural log to do a little bit of simplification here. So this is e to the natural log of 3 plus e to the negative natural log of 3 all over 2. So I know that first term, e to the log of 3, is just 3, and that second term, well, that can become e to the natural log of 3 to the negative 1 power over 2. So I have 3 plus 1/3 over 2, which with a little bit of work I could simplify to 5/3. Okay, so we see that we can combine these hyperbolic functions with logs and end up using some of our log rules in there to get some simplification. Here's a couple other examples here. Let's say I wanted to look at the value of hyperbolic tangent of 0. Remember that hyperbolic tangent is defined in terms of our hyperbolic sines and cosines. This would be hyperbolic sine over hyperbolic cosine. So that means I would have to convert to my definition. So remember that hyperbolic sine is e to the x minus e to the negative x all over 2. So this would be e to the 0 minus e to the negative 0, which we know is just e to the 0, all over e to the 0 plus e to the negative 0. So we would have 1 minus 1 here over 1 plus 1. So we would see that hyperbolic tangent at, of 0 is equal to 0, which agrees with that graph that we had before. Okay. And what about hyperbolic tangent of 1? Well, here I would have e to the 1 minus e to the negative 1, if I just go straight to plugging it in with the definition. Oh, excuse me, I missed a step here. These would be over 2, and this would be over 2. And when this canceled here, let's see, this is going to be minus. So this will end up being, yes, just e to the 0 minus e to the negative 0 over e to the 0 plus e to the negative 0. So that does end up being 0. Sorry, I forgot about our little divided by 2's. So let's be more careful over here. We're going to have this quantity over 2 divided by e to the 1 plus e to the negative 1, again, all over 2. So we'll see how those 2's will cancel. So I've got e minus 1 over e all over 2. Then that would be times 2 over e plus 1 over e. When I divide by this fraction, I'm multiplying by the reciprocal. So that's why those 2's cancel. So I would have e minus 1 over e plus 1 over e. And that would be my value of tangent. So with these hyperbolic functions, we have a whole new set of trig identities, which often resemble the trig identities that we've already become familiar with. But we can now prove these hyperbolic identities by converting to the definitions of these hyperbolic functions. So this is something that we do a fair amount in this section, so we want to get some practice with some examples. So if I want to prove that some identity statement is true, what I want to do is start with one side of the identity and then manipulate that side by showing its equivalent through various steps to the other side of the identity. And usually I want to start with the side that's a little bit more complicated and then work to simplify it. So here I'm going to start with 2 hyperbolic sine x hyperbolic cosine and then substitute in my definitions. So I'm starting with this right-hand side, and I'm going to try to show that that right-hand side is equal to that left-hand side. So I have 2 times, well, this is e to the x minus e to the negative x all over 2 times e to the x plus e to the negative x all over 2. Okay, so some of those 2's cancel, so I still have a 1/2. And then I want to multiply those 2 quantities together. So I'm going to have e to the x times e to the x, which gives us an e to the 2x, and e to the x times an e to the negative x, which is going to end up being an e to the 0, minus an e to the negative x times an e to the x, and then minus an e to the negative x times e to the negative x, which means I'm going to add those exponents. So you have to make sure you're comfortable with your exponent rules when we're doing these kinds of problems. So notice here, I don't even have to simplify those. Those are both the same term. I have one positive and one negative, so those cancel. So I have 1/2 here, e to the 2x minus e to the negative 2x. And if I want to write this exactly how it would look in our definitions here, I could write this as e to the 2x minus e to the, make it very clear that that negative's on the outside, e to the negative 2x all over 2, and then I can recognize that this is exactly hyperbolic sine of 2x, where 2x has been plugged in the power there. Okay, so this is our proof that 2 hyperbolic sine of x, hyperbolic cosine of x, is equal to the hyperbolic sine of the quantity 2x. Okay, so this is a kind of thing that we'll often do in this section. And let's just see, before we talk about a few more identities, I was just going to say a little bit about why we have this name of hyperbolic, what this has to do with a hyperbola. And that is the connection here, that there's a relationship to a hyperbola. So remember that for our regular trig functions, we know there's a relationship between our trig functions and the unit circle. So if I take the unit circle, then I can talk about a point P on the unit circle having coordinates cosine t, comma sine t, or sometimes we say cosine theta, comma sine theta, and this is the x-coordinate and y-coordinate along the circle where we have some angle t here represented. We also know that the equation here of this unit circle can be written as x squared plus y squared equals 1. Okay. It also turns out that if we use the area of a circular sector formula, remember that the area of a circular sector is pi r squared times pi over 2 pi. Okay, so if we have our circle here of radius 1, we have pi times theta over 2 pi, or theta over 2. And since I'm talking about an angle t instead of theta, let me replace it here. So the area of that sector is t over 2. Okay, so this area is t over 2, or we could say t is equal to 2 times the area. So we have a connection here between this t and this point cosine t comma sine t, the equation of the circle, and this being t being twice the area of that circular sector. So the reason that we're drawing that connection is that when we talk about our hyperbolic functions, if I have a hyperbola, now a hyperbola has equation x squared minus y squared equals 1. And it turns out that if I have a point P here on the hyperbola, that point P can be expressed as hyperbolic cosine, t, comma, hyperbolic sine t, where if I draw this hyperbolic sector, where t is equal to 2 times the area of the hyperbolic sector, that this shaded region here is making. So there is a connection here that these hyperbolic functions have this relationship to the hyperbola curve, like with our trig functions have this relationship with a circle. Okay, and one identity that we can get out of this, which you'll see me write on the next page, is that hyperbolic cosine of t minus hyperbolic sine squared of t is equal to 1. Just like out of our relationship between our regular trig functions and the circle, we have our cosine squared t plus sine squared t is equal to 1. So we have a slightly different identity when we're dealing with our hyperbolic trig functions. Okay. So we have now a reason for this name, and we also see, here's the list of several identities that we have. There's lots of other identities that we can now get from our hyperbolic trig functions. So we have some that just have to do with what happens if we plug in a negative version of x. We've got some identities here, like our hyperbolic cosine squared minus hyperbolic sine squared being equal to 1, that are similar to our Pythagorean identities. And we've got some identities here for what happens when we want to add an x and a y within hyperbolic sine and within hyperbolic cosine. Now if we wanted to prove this identity here that I stated on the previous page, we could also use our definition. So we'll just go ahead and do this just for more practice with these definitions. This is e to the x plus e to the negative x over 2, and hyperbolic sine is our e to the x minus e to the negative x over 2. So if I want to find what these values squared are, I'm going to have to, oops, I want a negative sign here. I'm going to have to square each of those quantities. So I would be looking at e to the x plus e to the negative x over 2 squared minus e to the x minus e to the negative x over 2 squared. So by being careful with my exponent rules here, I'm going to have an e to the 2x, and then I'm going to get a plus 2 e to the negative x, e to the x, plus e to the negative 2x. And this will be, let's see, minus, and I'll have parentheses here, e to the 2x minus 2 e to the negative x, e to the x, and then plus an e to the negative 2x. And this would be all over 4, because I already have a common denominator here. So let's see, how does this simplify? Well, e to the negative x times e to the x would just be an e to the 0. So I'm going to have an e to the 2x plus 2 plus e to the negative 2x. Then this minus sign gets distributed, so we have minus e to the 2x. And then let's see, this will be plus 2, because again, this e to the negative x times e to the x would be e to the 0. Excuse me. And then I'd have this minus e to the negative 2x, and this is all over 4. So I notice we get some cancellation, e to the 2x and minus e to the 2x, e to the negative 2x and minus e to the negative 2x. So then I've got a 2 and a 2 in the numerator, so I end up with 4 over 4, or I see that it's equal to 1. So using the definitions, we can see how this identity is true. And again, we could show all of these other identities and many more by just using our definitions. Okay, so the one other topic that I'm going to mention in this video lecture is a little bit about the derivatives of these hyperbolic trig functions. So let's say I wanted to find the derivative of hyperbolic cosine. Well, I know that hyperbolic cosine is again e to the x plus e to the negative x all over 2. So if I want to take the derivative of that, I just need to use my rules for the derivative of my exponential functions. So I'm going to have e to the x minus e to the negative x over 2, because that constant would just stay out in front. Remember, I can just look at this like the derivative of 1/2 e to the x plus e to the negative x. So the derivative of a constant times something is just the constant times the derivative of that next piece. And then we look at this and we recognize it as hyperbolic sine. So we see that the rule for the derivative of hyperbolic cosine is hyperbolic sine. And notice that that's different than for our usual trig function, because we know the derivative of just cosine x is negative sine x. So here we have a positive hyperbolic sine as our derivative of cosine. Okay, so we could do this for all of the different hyperbolic functions, but just to summarize, these are now our derivative rules for the hyperbolic functions, and so these are a new set of derivative rules that we need to commit to memory. So we've got the derivative of hyperbolic sine is hyperbolic cosine, derivative of hyperbolic cosine is hyperbolic sine, so it's just what we always wanted to be true. The derivative of hyperbolic tangent is hyperbolic secant squared. Okay, so we notice that some of these follow patterns that we've seen before. We just have some sign differences. The derivative of hyperbolic cosecant is still negative, hyperbolic cosecant, hyperbolic cotangent. The derivative of hyperbolic secant, however, is negative, where in the regular derivative of secant, it's positive. So we have, in this row, we have some sign differences. And lastly, we've got the derivative of hyperbolic cotangent of x is negative hyperbolic cosecant. So these look similar, we just have some sign differences for the derivatives of hyperbolic cosine and hyperbolic secant. So we just want to look at one example where we practice using these derivative rules. So here I want to find the derivatives of these two different functions. So for the first one, I'm looking at the derivative of hyperbolic tangent of 1 plus e to the 2x. So I need to take the derivative of hyperbolic tangent, which is hyperbolic secant, so I've got secant h squared, of my inside function. And then I'd have to multiply it times my derivative of 1 plus e to the 2x, which would just be 2e to the 2x. And so that would be my derivative of f using the chain rule. And then if I wanted to take the derivative of the second quantity here, again I have to use the chain rule, so I got to do the derivative of that outside function. Derivative of hyperbolic sine is hyperbolic cosine. I'd have to evaluate that at hyperbolic cosine, and then multiply times the derivative of hyperbolic cosine, which we just showed earlier was positive hyperbolic sine. Okay, so these aren't too bad. We get to use a lot of things that we've already learned, but we'll talk more about some of the applications and interesting ways in which these hyperbolic functions are used. Please let me know if you have any questions.